Good day to Doctor. My name is Jagadesh and today I'll be presenting my project which is File System Organizer. The primary objective of this project is to build a system that can efficiently manage a file system just like the one in your computer. A file system needs to be good at very two things. First, it needs to handle hierarchical operation, things like navigating from one dictionary to another. Second, it needs to be able to perform a global search, finding a file by its name, no matter where it is in the system. A key feature in my design for this project is flexibility. To prove the system robust, I designed it to work in two ways. It can be initialized with a simple built-in dataset for easy testing, or it can dynamically build its entire structure from a real-world Kaggle data folder. So, in order to create this project, I used three main data structures. First, we have the file system tree, which acts as the hierarchical backbone of the entire system. The tree was a natural choice for modeling the file system structure. Its main purpose is to manage the parent-child relationship between directories and files. The most important design choice I made here was how a directory stores its children. Instead of a simple list, I used a dictionary, which is a type of hash map. The benefit of this is immense. It gives us one average time to find a child within the directory. This means that navigating a div path like documents or reports is extremely fast because at each step, the next folder is almost found instantly. If I had used a list here, the system would have slowed down dramatically as directories grew larger. Next, we have the hash table. The hash table's purpose is to provide instant system-wide and case-insensitive file searches. There are two key design choices here. First of all, file names are stored in lowercase keys for case insensitivity. Second, the values are a list of nodes. This is important because it allows the system to handle duplicate file names appearing in multiple directories. So the final data structure that I used is linked list. So it is used for command history features, and my key design choice was to add new commands to the front of the list. Benefit here is that adding to the head of the linked list is a classic O of one operation. This is perfect and a real-world use case that demonstrates the data structure strengths without slowing down the core system. Next, let's look at the live demonstration of this project. So let's look at our live demonstration of the file system organizer. The first step is to upload the Kaggle file. And then the next step is to unzip the Kaggle file and display the data. These are the data inside. So the next is we convert the folder and file into a simulated file data system. So this is our converted file. This is how it looks like. And next is the implementation of the linked list representing the file system in tree nature, the implementation of the hash table, and this is the main application class where all the functions of the system is here. So next is the main execution of the program. So in this block, the main execution is made to run the entire program, and there is a simulated built-in data in this section to make sure the user has the flexibility whether to test their own data or the simulated data. So this is the option that user has, whether they can use the built-in data or the Kaggle data. Let's go with our Kaggle data that we uploaded earlier. These are all the options that we have. First option is to list the contents, the directories of our data. This is our directories inside the data we uploaded. And now let's look at the display of our data in tree structure. So we can see here, this is our data in simulated tree structure. And now we can choose to enter which one of the directories. So let's choose the politics. So after we enter one of the directories, we have the option to add item, delete item, or rename the item inside the directory. So let's add one item inside the politic directory. We add a file name. We can enter a random file name and the size. So we can see here our system has successfully added our new file, and we can see in this tree structure also our file has been added, medical name inside the politics directory. We can rename this file if you want. Let's say in this scenario I've accidentally put the wrong name. Instead of putting politics, I've put medical. So let's change that. So we see here that our file has been successfully renamed, and we can check free system. So yes, this is our rename file, and we can also delete this file. So yes, we can see the file has been deleted. We can look at the tree structure, and there is no more appearance of politics 9 in our file system. Next is we can see is the option to see the specific details for our specific file. So let's look at the details for this file. So here are the specific detail, the name, the type, the full path of the file, and the size of the file. And next we can search for a file in our entire system, not just one directory. So let's say right now we are in politics directory. Let's say we want to search a file outside this directory. Let's say we want to search for medical. So we can see here there are 4 medical files in different directory. There are 4 files here. If we look at the full display tree, we can see there are 4 files here. So this proves that the system can detect the file that we want to find successfully. And the last option we have is to list the size range of file. So this is for the entire system. So we enter the minimum size that we want to find. Let's say 0.5 kilobytes, and the maximum is 3 kilobytes. You can see here there are 14 files found within the range of 0.5 to 0.3. So next we can look at the command history, which is the final action that we can do this file manager system. So this feature, this action is implemented by linked list. And the purpose of this function is to show our commands that we made or the users made. So finally, before exiting our program, the user is given a choice whether to save their session or not. So we can save our session. So we have looked at the live demonstration of the project. Next, let's move forward with performance summary. So operation like path, like cd and add, which uses tree, are very fast, depending only on the depth of the path, not the total number of paths. User-friendly parsing is also efficient because while it iterates, it only iterates through files and not every single node in the tree. And adding the command history is an instant of one operation thanks to the linked list. And finally, displaying the full tree is proportional to the number of nodes, which is the expected behavior. Next, let's look at the key features and robustness of this system. Beyond just the data structures, the project also focuses on being robust and user-friendly. So one of the key features is the search and set functions are designed to do what users likely means, like searching case insensitively or system-wide if a file isn't found in the system. Second is the most important one where the system is designed not to crash. It has comprehensive error handling that catches invalid input or non-existent files and provides a very clear, helpful message instead of failing. And the persistence of this feature with Pickle allows users to save and load their work reliable across different sessions. So in conclusion, this project successfully built a full featured file system organizer by combining three key data structures. By using different specialized data structures, which is a tree for structure, a hash table for speed, and a linked list for utility, we can create a system where the strengths of one cover the weakness of another. And the final result is a fast, functional, and a reliable application that proves the practical value of this fundamental file system manager project.